Okay, any questions? Now, okay, so what we have achieved up to now, since the beginning of the semester, now we have a way of describing our system in terms of these Hilbert space kets. We know how to do translations, and we had identified our momentum operator. We know how to make translations in time so we can determine the time evolution of our kets. So that's basically what we had done up to this point. Now, one question is, okay, so what? So at the end of the day, we are not really observing the kets themselves. So what we would be most of the time observing, if you just imagine a realistic experiment, you basically create many copies of the same system, you make many measurements on your system, you take some kind of an average. That is what you measure most of the time. And so that is also what we will be interested in calculating. So not the kets themselves, but how do, let's say, we have an operator A, and so its expectation value as a function of time is given by this expression. This is basically how it will evolve in time. Well, we know how the kets evolve in time. So this is alpha t0, u dagger, tt0, a, u tt0, alpha t0. But once you write this expression, you basically have two different means of interpreting the same result. So you see here, on the left-hand side, A is independent of time. The ket evolves in time. This is what the left-hand side is telling me. If you look at the right-hand side, so here we have this operator. That operator evolves in time, whereas the bra and the ket are independent of time. And you see they are equal. So since they are equal, you can just use whichever perspective you like, or whichever picture you like. So these are what we call the different pictures. They are describing the same thing. So the left-hand side is what we call the Schrödinger picture. The right-hand side is called the Heisenberg picture. Now the operator, the time evolution of the operator A, let's say A of t, is given by this expression. Or let me put the H over here, meaning that it is my operator A in the Heisenberg picture. Let me put the S over here, that is the operator A in the Schrödinger picture. So this is how the different operators in different pictures are related. Now, one advantage of the Heisenberg picture over the Schrödinger picture is that, you see, if you want to evaluate the time evolution of this expectation value, you first need to determine the time evolution of your ket first. So depending on the time evolution of your ket, you get the time evolution of the operator A. But here, the time evolution of A is independent of your ket. Whatever system is your ket, that is your operator. That is your time evolution. You just apply that time evolved system to any ket that you like. Let's do an example. Or before doing the example, let's look at, okay, so before we looked at how what is the time derivative of this unitary operator u, or what is the time derivative of our cats in the Schrödinger picture. Now let's look at what is the time derivative of these my operators in the Heisenberg picture. They will be easier to solve. Well, this will be equal to, you see, the time dependence is only in the u and the u dagger. So this will be equal to derivative of u dagger by dt a s u plus u dagger t t0 a s du by dt. We had already calculated that du by dt is just 1 over I h bar of u. So the u dagger by dt will be just minus 1 over I h bar u. So there is a h over here, u times h over there. U dagger times h. Or, well, let us put them over there in our differential equation. dA by dt is equal to minus 1 over I h bar u dagger h a s u plus 1 over I h bar u dagger a h u. Well, I will look at the case where the h and these equations are anyway valid when h and u commute with each other. So this same expression I can write as 1 over I h bar u dagger a u times h minus 1 over I h bar h u dagger a s u. I also changed the order of the terms. But you see, this is nothing but my operator in the Heisenberg picture at the time t, and this is the same operator. Which tells me that the time derivative of my operator is nothing but 1 over I h bar times my operator, its commutator with h. Now, when you take classical mechanics or analytical mechanics, if you haven't taken already, you will see that this is very similar to our Poisson's equation, where the time derivative of any observable was given by its Poisson bracket with the Hamiltonian. This is exactly the same result. Now let's do the application. Let's look at our free particle. What will be our momentum operator as a function of time, our position operator as a function of time in this Heisenberg picture? I'm dropping the superscript h. Now, the Hamiltonian for the free particle, we will just assume that it has this form, p squared over 2m, p being our momentum operator. Well, how do we know that it is just p squared over 2m? Well, we don't know what the Hamiltonian is in quantum mechanics, so you just have to make some assumptions about Hamiltonian. But what we do know about quantum mechanics in general is that it should also explain whatever the classical mechanics explains. It should contain classical mechanics because basically classical mechanics has been tested for centuries. And we know that it works, at least whenever we can apply. So somehow classical mechanics should be contained in the Hamiltonian. For a free particle, we know how a free particle behaves classically. So the easiest way to make sure that the classical results for a free particle is also contained in the quantum mechanical formulation would be just to assume a Hamiltonian operator to have more or less the same form. So that is why we are taking p squared over 2m. So the time derivative of the position operator. This should be equal to 1 over I h bar A, X, and H. This is 1 over 2mi H bar X and P squared. This is 1 over 2mi H bar xp times P plus P times xp. Are you familiar with this computation algebra? You see, the thing that I will be using quite often in term for commutators will be commutator of A and B is minus the commutator of B and A. Commutator of A, B, product C is commutator of A and B multiplied with C plus B times A and C. This is the second one that I have used in the second line. And furthermore, A, B, C plus B, C, A plus C, A, B, these double commutators, they have to be 0. This is called the Jacobi identity. Now let's continue. So dx by dt in the Heisenberg picture, this is equal to 1 over 2mi h bar. What is the commutator of x and p? I h bar. I h bar p plus p times I h bar. This is 2I h bar times p divided by 2mi h bar. 2I h bar, they cancel. So dx by dt is nothing but p of t over m. Well, that which in classical physics we identify as the velocity. Now this is just a classical result. The only difference being here x and p are operators, not observables, not functions, let's say. Now let's look at what about the p. This should be equal to 1 over I h bar. It's just 0. Well, we can solve these operators, these differential equations. This just tells me that p of t is nothing but the p at the time 0. So dx by dt is equal to p at the time 0 over m. So this tells me that x of t is equal to p0 over m times t plus x at 0. Well, Hamiltonian is always constant. You see, what is dh by dt? It is 1 over I h bar h h. This is 0. But keep in mind, we had started by assuming that Hamiltonian doesn't depend on time. Doesn't have any explicit time dependence. If there was an explicit time dependence, we should have added some partial derivative of the Hamiltonian with respect to time. But in that case, we have to modify significant portions of our derivation. Most of the results will still be valid, but yeah, to be careful when you are driving them. Now, let's look at one more thing. This is our x of t. What about the commutator of x at two different times? Is it 0 or not? Let's see. This should be equal to p0 t over m plus x of 0. No, p0 times t prime over m plus x of 0. Well, the non-zero terms in this commutator will be p0 x0 commutator multiplied by t and m plus t prime over m x0 p0 t over m p and x commutator is minus I h bar plus t prime over m, this is I h bar, so this is equal to I h bar over m t prime minus t. Now let's see. What about delta xt squared multiplied with delta xt prime squared expectation value? This is always larger than or equal to 1 over 4 h bar squared delta t squared over m squared. So this is 4. So you see, even if you start with a state that is highly localized, let's say at the time t prime, the uncertainty in its position at a later time t will increase with time. So it will not stay localized.
Konumu ölçtüğünüz zaman bunların diyor aynı olmasını bekleyemezsiniz diyor. Çünkü diyor translation operatörü burada etki ediyordur. Yani ölçtüğünüz x0'dan sonraki ölçtüğünüz x arasında bir belirsizlik olması gerekiyor. O zaman burada bunu yapan şey translation operatörü mü yoksa time evolution operatörü?
This is the time evolution, not the translation. The time evolution just spreads your wave. Well, in a sense, you see, this is also related with the momentum. Well, you see, if you look at the derivation, it is basically related with the momentum coordinate commutation relation. And also to the fact that if you want to create a localized state, you are basically superposing many momentum eigenstates, not just one. And each one of these momentum eigenstates are moving at different speeds. So since they are moving at different speeds, even if you start with a wave that is localized, with a kit that is localized at a single point, they will be moving out at different speeds. So you see the uncertainty increases. And you are also superposing kits with momentum in one direction and also in the other direction. No, position and momentum uncertainty is not due to time evolution. No, it's due to the nature of the states that you create. It's not a measurement problem. It's just they do not exist momentum and coordinate, at least according to the Copenhagen interpretation, let's say. It's not a problem about our measurements. No matter how precise you make your measurements, that uncertainty relation stays there. Now, this uncertainty over here is due to time evolution. Of course, you can also relate it to translation operator, because here we have a free particle whose Hamiltonian is given by the momentum, which is the generator of time translation. So time evolution will involve position translation. It's not the same thing, but they are kind of related, let's say.
O zaman o aradaki bağlantı dediğimiz gibi her farklı kitin farklı momentum olacak.
If you write in terms of momentum eigenkets, there are many terms in that superposition. In fact, if you want to localize your initial state to a position with an uncertainty delta x, the momentum components should be spread in a momentum range given by delta p. So the smaller the delta x is, the larger the delta p should be. You should be adding more and more momentum components to create a more and more localized ket. Well, there is one part which was kind of shaky in our derivation. You see, in some places I wrote explicitly the time t, in some places I erased it, in some places I didn't even write it. Let's see. For example, let's just look at this expression, the dpt by dt, equal to the commutator of the momentum at the time t with the Hamiltonian. And then I just said that, let me ignore the argument t. So it's p and p squared over 2m. At which times? You see, now it starts to it has importance. You see, x, for example, at different times, they do not commute. So commutation relations are now time dependent. So you have to be careful about which commutator you are talking about at which times. So let's look at this one. What are the times over there? Or in fact, let me put it somewhere else. Here, I didn't write the time explicitly, but which time are we talking about, the Hamiltonian? Well, if we were to define the Hamiltonian in the Heisenberg picture at the time t, let's say, we should have defined it as e to the power I over h bar, h t minus t0, multiplying the Hamiltonian in the Schrödinger picture, multiplied by e to the power minus I over h bar, h t minus t0. But you see, the Hamiltonian commutes with those operators. So this is nothing but hs. So whatever the time over there, you can just put whichever time you like, basically. So here I have the operator at the time t, let's say. Just to be consistent, since I can choose whichever time I want, Hamiltonian is constant in time. Just to simplify my life, I can just talk about the same time everywhere over there. So when I come over here, this is the momentum at the time t, and this is p squared over 2m at the time t. So they are both at the time t's. Now, what about the commutator of two operators in the Heisenberg picture, let's say at and vt? What can I say about this one? Well, let's write it down explicitly. This is a of t, b of t, minus b of t, a of t. This is equal to u dagger a u. This is a of t. B of t is u dagger a of u. Again, B of t is U dagger, B U. A of t is U dagger, A U. But you see, these are, oh, sorry, this is B. Now, this product is just 1. Similarly, this product is just 1. So this is nothing but U dagger, A, B, U. Yep. So basically, if you are talking about the commutator of two operators at the same time in Heisenberg picture, you can just calculate the commutator as if it was in the Schrödinger picture. And instead of at the end, whatever operator you have, just interpret it as your operator in the Heisenberg picture. But keep in mind, these are commutators of two operators at the same time. So basically, P of t, for example, P of t, x of t. What is this commutator in the Schrödinger picture? Minus IH bar. They are just constants, so they are the same both in the Heisenberg picture and also in the Schrödinger picture. P of t, x of t prime, on the other hand, is not minus IH bar. Because here I have the commutation relation of two operators at different times. Let's see if it is possible that they will commute at a given time for our free particle. We can calculate it. P of t, x of t prime. This will be equal to, for the free particle, P of 0. Well, x of t is P of 0 over m times t plus x of 0. Well, the first P0 commutes with P0 over m times t. So this is P0, x0. This is equal to minus IH bar. Well, let's say a priori. It just turned out to stay the same for the free particle. The uncertainty relation doesn't change. So? Well, you see, what does this tell me? Well, you can just say, let's say, suppose you create a momentum eigenstate at t equal to 0. Okay? So delta p at 0 is 0. But this is telling me that I have no idea about the position of this particle at any time. So if we state this particle at t equal to 0 as a definite momentum state, my particle doesn't just go and localize at a given point. Delta x is infinite at all times. Or I can just look at it the other way around. Let's say I have a very localized particle at the time t is equal to 0. So I don't know its momentum now. If I let it evolve, I don't know its momentum at a later time also. Delta p is always infinite. For example, classically speaking, let's look at a classical example of a potential well. Now this is a free particle, but let's look at the potential well, harmonic potential with some dissipative force. Now, no matter how much I know about the initial position of the particle, eventually the particle will be at whatever the initial momentum is, it will be at the minimum of the potential eventually. So eventually, at a later time, the particle will be localized at the minimum of my potential. So basically, this can happen in classical physics. But definitely it doesn't happen in this problem. My particle by itself does not get localized at a given point. Now let's see what happens if we have some potential. This was for a free particle.
Orada time, anytime t'de hep aynı zaten değil mi?
True.
Onun
Correct.
için ben t'yi, momentumdaki t'yi, momentumdaki t'ye göre ayarlarsam işte öyle zaten.
Well, you see, this t over here is the t over here. So I don't really have a freedom over there. But the time in the Hamiltonian, I can choose whichever I want. But you see, using this property, where was it? Okay, using this property, I can calculate the equal time commutation relations. You see, commutation relations at different times, I have to derive them. But equal time commutation relations are easier to write down. That's why I'm taking the Hamiltonian also at the same time, t. By writing a time in the Hamiltonian, I'm basically saying that, okay, the momentum, it will be time dependent. Whatever position appears in my Hamiltonian, it will be I'm basically replacing all the operators in my Hamiltonian by their analog in Heisenberg picture at the time t. This one. Yeah, a priori diye, yani baştan, I cannot say it without calculating. For example, I can say that equal time commutation relation of p and x will always be minus IH bar, whatever our problem is. But the non-equal time commutation relations of p and x at different times, it doesn't have to be minus IH bar. Well, for a free particle, it just turns out to be minus IH bar. For a non-free particle, it won't be minus IH bar. Or, well, maybe, we will see. We will see. Well, we will try to see, let's say. Well, the Hamiltonian will be p squared over 2m plus v of x. Well, let's start with dx by dt. This will be 1 over I h bar, x and h. Well, I'm kind of dropping any explicit time dependence. I'm not showing it explicitly, let's say, because all the operators, from now on, I will treat all the operators at the time t unless I explicitly specify it. So here x is x of t, h is h of t, etc. So this will be equal to 1 over I h bar, x of p squared over 2m, plus 1 over I h bar, x and v of x. Well, x and v of x, they commute. So this is just 0. We had already calculated the other part, dx by dt is just p over m. So whatever the potential is, the time derivative of the position operator is the momentum operator divided by m. Now let's look at the p by dt. This is equal to 1 over I h bar P and H, 1 over I h bar P and P squared over 2m plus 1 over I h bar P and V of x. Well, this is 0. dP by dt is equal to 1 over I h bar P and V of x. Well, we will show it in a moment. This is 1 over I h bar minus I h bar del V by del x. So this is equal to minus del V by del x. Okay, first of all, of course, we have to first specify what we mean by this derivative with respect to an operator. It's not really a derivative with respect to an operator. You see, v is a function. Let's say v of y. Y can be a number or an operator. If you put an operator, we have to interpret it as a Taylor expansion. Now, what we mean by del v by del x is first we take the derivative of this function with respect to its argument, whatever it is. And then after we take the derivative, we just replace x with the operator. We are not really taking the derivative with respect to an operator. Well, this is the classical equation. You see, that's basically what we are trying to show here. Classical physics is incorporated in quantum mechanics. But in classical physics, we have the position as a function of time, momentum as a function of time. In quantum physics, we have the corresponding operators. And since the operators satisfy the same classical analogs, the equation of motion satisfied by the operators are equal to the classical equations of motion. What we will be observing will be expectation values. So since the operators satisfy equations similar to the classical equations, the expectation values will satisfy exactly the equations that we have in classical physics. So the expectation value of del v by del x, keep in mind that's an operator. If you want, you can identify it as some kind of an average force acting on my system. If you want, just call it the force operator. You see, even in analytical mechanics, rather than using the concept of force, we use the concept of the potential and express everything in terms of the potential. Of course, you can relate it to Newton's concept of force. No, I mean, whatever the potential is. You have a potential. For example, let's do an example of the harmonic oscillator. Yes? Nothing. For practically nothing. But this is basically what you are doing. You see, the concept of differentiation with respect to an operator doesn't really make too much sense. So that's why I'm saying that here I'm not differentiating with respect to an operator. For example, momentum operator. Well, you see here, okay, let's just do a couple of steps before applying this to harmonic oscillator. Here what I used, P and V of x. I said that this was equal to minus I h bar del V by del x, and x and V of some function of P. This will be equal to I h bar del F by del P. So you see, we will be using the momentum operator in coordinate space. It is minus I h bar del over del x. So what is the meaning of F minus I h bar del over del x, its derivative with respect to minus I h bar del over del x. It doesn't really have a meaning. You see, the differentiation, we usually define them with respect to numbers or arguments that take numerical values. That's basically what I'm trying to specify over here. Practically, you are used to doing it the correct way without really knowing what you are actually doing. So let's just prove these two identities. Well, I will prove one of them. The rest is kind of straightforward, the other one. Let's start with this one. Well, this is equal to the commutator of P. Keep in mind the functions of operators, we always interpret them in terms of a Taylor expansion. This is my V of x. This is equal to sum over n, a n, p x to the power n. Now, p x to the power n. This is equal to, now let's do a couple of examples. P times x. So this is minus I h bar times 1, which is minus I h bar del x by del x. Px squared. This is equal to px times x plus x times p of x. This is minus twice I h bar times x, which is minus twice I h bar del x squared by del x. Px to the power n. This is equal to px times x to the power n minus 1. So let me write it in this form. This is px, x to the power n minus 1, plus x, p of x to the power n minus 1. This is minus I h bar, x to the power n minus 1 plus x, p of x to the power n minus 1. Now I will use induction. My claim will be, you see, up to the term n minus 1, I will claim that this will be equal to minus I h bar del x to the power n minus 1 by del x. Well, this definitely holds for n is equal to 1. If n is equal to 1, the commutator is 0. The right-hand side is 0. It holds for n is equal to 2. If we say n is equal to 2, px commutator is minus I h bar del x by del t. It holds for n is equal to 3. If n is equal to 3, it is just x squared here. At the top line, we have shown that it is correct for n is equal to 3. So it holds for n is equal to 1, 2, and 3. I will assume that it holds for up to some number n minus 1. And then I will try to prove that it holds for x to the power n, the next one. So let's see, p of xn is equal to minus I h bar x to the power n minus 1 plus x times minus I h bar times n minus 1 times x to the power n minus 2. So this is minus I h bar n times x to the power n minus 1 minus I h bar derivative of x to the n divided by del x. Now let's see what I have done. If it holds for n minus 1, This is what I had proved. If it holds for n minus 1, it also holds for n. That is what I proved in these last 3 lines. It holds for n minus 1 is equal to 1. So it holds for n is equal to 2. So it holds for n minus 1 is equal to 2. That means it holds for n is equal to 3. If it holds for n is equal to 3, then it holds for n is equal to 4. If it holds for n is equal to 4, it holds for n is equal to 5. So basically it holds for all integers. Well, let's go back. So I was over here. So this is equal to n a n minus I h bar, derivative of x to the power n by del x. Is equal to minus I h bar del over del x, sum over n a n x to the power n. I just took the derivative out of the summation sign. But this is nothing but Vx. So if I calculate the commutator of momentum with a function of x only, that's the only thing I have. The v of x has to be a function of x only. Then I can just write the momentum as the derivative acting on v only. By the way, this relation you also have in classical physics, if you just consider the Poisson bracket of the momentum with a function of the coordinate. You will get exactly the same relation. How many of you took analytical mechanics? Well, I mean, just keep these relations in mind when you take the analytical physics. Any questions? Well, on Wednesday, as an exercise, we will do the harmonic oscillator. How does it change with time, the operators?
Boyzun mevcutlardan giderken hemen bunların potansiyel zaten sadece x'e bağlı olduğu için oradaki differential parameter sadece x üzerine inecek.
Biraz önce AVD operatörleri sanki tahmin yapmıştık.
Hı hı.
Sonra araya inter operation yapmıştık. Tam da mesela inter operator'da şeyin yani bu bize neyin bilgisini veriyor kavrayamıyorum. Time evolution arasındaki bağlantıyı kuramıyorum.
Let me add the indices over here. These are the Heisenberg, these are the Schrödinger picture operators. Now, what we have achieved in all this derivation, we basically said that up to this point, up to today, we were always looking at the evolution of the kets. So the kets were time dependent, so I have my system is evolving in time. So the ket corresponding to my system is also evolving in time. So that kind of made sense to us. But now, today, what we have seen is, at the end of the day, we want just some expectation values. Those are the things that we can actually compare with experiment. But when we looked at the time evolution of these expectation values, we had some choices. We are not, the formalism doesn't really dictate which choice we should, which perspective we should have, which picture we should pick. Any picture will be valid. So the picture in which we have our cats evolving in time, that is what we call the Schrödinger picture. But we said that there is this alternative picture in which the cats are at rest, they don't evolve in time, but the operators are evolving in time. So the time dependence of the expectation value of any operator, any observable, is due to the evolution of the operator itself. And keep in mind that we are not talking about explicit time dependence of the operator. Now, for example, the operator can be the momentum operator multiplied by t squared. That operator has an explicit time dependence. But that operator also has an implicit time dependence if the momentum operator that changes with time. Okay, so here I'm talking about implicit time dependencies. So the operators are evolving in time. Well, of course, in this case, we are kind of losing this intuitive understanding that if my state is evolving, the cat should be evolving in time. So that is kind of lost. But there is an advantage to this new formalism. The equations that govern the time evolution of my operators, they are almost exactly the same as the equations of motion I have in classical physics. So this Heisenberg picture makes it more explicit that quantum mechanics is, in fact, somehow incorporated in this quantum mechanical picture. So in classical physics, we have the time-dependent x and momentum. In quantum physics, we have the time-dependent position operator and momentum operator. And they satisfy, the equations they satisfy are almost identical. So that is what, I mean, due to this equality over here, whichever picture you use, they should give you the same result. But one operator, one formalism, the Schrödinger formalism, is more intuitive if you like the idea that the system is evolving, so the cat is evolving. The other Heisenberg picture is more intuitive if you like the idea of working with x of t and p of t as a function of time.
Sonuçta operatörleri biz tool olarak kullanmıyoruz.
Okay.
Ben neden tool'un time evolution'una bakayım ki? Anlamak istediğim onun bir anlatıyor mu?
Well, you see, what I want to have is calculate these things. I cannot measure my states. I cannot measure my cats. I can measure certain properties of my states. And those properties of my states, I can say, okay, my state is evolving, so those properties are changing. Or you can say, okay, my observables are evolving, so my observations are changing.
Observe ettiğimiz şey zaten önemli olduğu için artık onu ya state'i değiştirip oradan anlayacağız ya da operatörü değiştirip anlayacağız. Yine aynı şekilde.
Well, this is very similar to the idea that when we are talking about symmetries, you can either rotate your system or you can rotate your basis. This is basically the same idea. Exactly. That U operator either changes your operators or changes your vectors. You are free to choose one or the other one. Just pay attention that you cannot do both.
O zaman interior operatörleri sadece rotation gibi algılama tam olmuyor. Daha fazla bir şey. Sanki space'te tanımlıyor gibi bir şey.
It's a transformation. Well, most of the time you can write them in terms of rotations, though.
Çalıştığımız operatörler genelde birbirine rotasyon olduğu için aslında.
Now, unitary operators are like rotations, not other operators. Momentum operator is not a rotation. You see, unitary operators do not change the magnitudes. That's why they are very similar to rotations. In a sense, unitary operators are just generalization of rotations to complex spaces.
şema düşündünüz mü? Klasik mekanikte evren dönüşümlere bakarken 3 boyutlu koordinat sisteminde bir tarafta koordinat sistemi çevirirken diğer tarafta vektör çeviriyoruz. Aynı mantık olarak bakıyoruz.
They are very similar. Well, of course, things are kind of getting more complicated. Here we have a base kets, we have the kets, we have the operators. So your example is more like whether you rotate the base kets or the coefficients. But I mean, the idea in this example is also very similar. You see, you have some quantity which depends on more than one thing. You either transform one of them or the other one. So in the case of the kets expanded in terms of the base kets and the coefficients, well, if you are changing your ket, that might be either due to the change in your base kets or change in your coefficients. And most of the time, just change in one you can write in terms of change of the other one. Here, basically, we have a similar idea. You either change your operators or you change your kets. Later on, we will see that we will be basically dividing the time evolution into two parts, for example. We will be both changing both the kets by part of a Hamiltonian and changing the operators by the remaining part of the Hamiltonian. So this is basically your freedom. So you are allowed to use your freedom to simplify your life as much as possible. You see, for example, in this formalism, once I determine the time dependence of my operators, I don't need to worry about the time evolution of my state. If I want to calculate the expectation value, let's say where we have it, so this tells me that average of x as a function of time in any state is basically the average of p at the same state, t over m, at the time 0, plus the average expectation value of x at the same ket. So you give me one ket, I calculate the momentum and position expectation values of that ket, and I know the position expectation value at an arbitrary time, even if I don't know my ket at that time. I don't need to worry about solving the time evolution of my ket. This equation, this operator identity, is valid whatever ket I use. That's also one advantage of this Heisenberg picture. We will discuss it later on. I just mentioned it to give you an example of the freedom we have. We are calculating basically the same thing, just using some different tools, some different perspective. And you are allowed to do whatever you want, as long as what you do is correct. Okay, so see you on Wednesday.